Okay, so let's do a count. I just want to do a count and see what's involved in this problem. This is exactly what you would do if you were going to solve it numerically, right? Full Navier-Stokes. So I have four equations for each region and 4 unknowns, U, V, W, and P. Okay, so I have 3 regions, so that's 12 equations, right? Then what's involved? Then I need to think about boundary conditions, and in addition, I need to solve these flows in different domains which are moving in time. And then I need to also determine these functions, S1 and S2. So how many unknowns? Well, we said we have 12 from the 3 regions, right? The 3 velocity components, pressure times 3, plus 2 interfaces. So it's 14 altogether. Those are the unknowns. Now, what about the structure of these equations? Well, this, what's shown here is what you do in X, right? Far away. Far away in X, not vertically, but far away, I could have things being periodic in X, right? So waves form and they're periodic in X. Or things could go to some steady states, right? So uniform flow or undisturbed interfaces and so forth. Or I may get a flow very far away, which is simply a function of y. This is exactly Darren's situation, right? Where it was a function of x and y. But if there's no structure, then it's a function of y. And then the pressures could also go to constants. So the question is, what boundary conditions do we need before we can close this problem and look for solutions? So let's see what happens. So each of these Navier-Stokes equations, and there are 3 scalar ones in each region, they have second derivatives, right? They have Laplacians. So in the y direction, I need 2 boundary conditions for each velocity field. Okay? Because I have boundary conditions in y. So the second order in y. So I need 2 in each region, and therefore I have 6 conditions. Right? I need 6 conditions in each region, and there are 3 regions, so I need 18 conditions. So I need to come up with 18 boundary conditions to solve this problem. So where do these come from? So I want to give you some details about where these come from before we get into analyzing them. So let's see. Well, mathematically, you need to go and think about the physical problem in order to identify what these conditions are. So here are a few things we know. We have no slip at solid boundaries, but we also have continuity of velocities, usually at liquid interfaces. Okay, so these are conditions we need to impose. And then additional physical conditions are balancing forces, a balance of forces at interfaces. This is where surface tension will come in and various other things. So we'll do the details of this in a second. And then thirdly, the interface is a material surface. It doesn't break apart. So I will get some kinematic conditions there. So what does that give us? Well, if we have no slip, so let me just do it for one of the boundaries. Y equals D is the top boundary. I have no slip there. For UVW, there are 3 velocity components. So I have 3 conditions there, right? And then I have 3 continuity of velocity conditions at this interface, another 3 there, and another 3 no slip there. Okay, so a total of 12. So I need 6 more. okay, in order to have a well-defined mathematical problem. So where do these come from? So let's see if we can formulate these. Well, these come from continuity of these forces I mentioned at the interface, because these two liquids are viscous immiscible, and they will exert forces at the interface. So I need a balance of these forces at the interface, otherwise the interface will break apart. So this is what we want to do next. So if I look at the whole continuity of stresses, but let me kind of derive that for you. So if I take any point in space, okay, this you can see in any book in fluid mechanics. So let me take any point in space, x0 say, vector, position vector x0, and then if I take any surface, any surface going at this point, containing this point, that has a local normal n, right? This is the normal n at this point x0, then this matrix times n, where this matrix is a stress tensor, will give you a force. Okay, so that's a force per unit area. So the only thing you identify is the normal, right? The point and the normal, and then locally there's a little piece of surface, and there's a force there. And the force is exactly this matrix times the vector n. What's this matrix? That's the stress tensor, and I've written it there. So think of this 3 by 3 matrix in 3 dimensions. So it's minus p delta ij, Kronecker delta, plus the viscous stresses. Okay, so this is the general situation in 3D. Let me show a picture of this. So this is a picture, kind of a little construction of what I just said. So here's my x0. So if I take a piece, an element of surface area, dA or whatever, with a local normal n, there's a force, Tn. Now, this is a viscous flow, right? So these flows are viscous. So let's just go back a second and notice something. So if I look at this stress and I drop viscosity, okay, there's no viscosity, so this term is gone, then the stress tensor is just minus p delta ij. So what does that say? It says that the force at this point is always going to be in a direction parallel to n, to the normal n, okay, which is what we learn in fluid mechanics. If you take any point in space, then there's always a force that's perpendicular to any surface in the fluid. The force will be perpendicular to it for inviscid flow. But because you have friction, this changes, and the force will be given by Tn. Okay, so how do I use this? This is very general fluid mechanics, right? So how do I use these ideas? By the way, this is another thing you can do to write down the Navier-Stokes equations. Okay, you just do a momentum balance now on a little volume of fluid anywhere in the fluid. But what I want to do is come up with boundary conditions at sharp interfaces where the viscosities change. They jump in value. Okay, or other things may change. All of this can be done for elasticity as well, when things change across material surfaces and so on. So the way we do this is we take this force that I know how to work out from at a given point and evaluate it at the interface. Okay, so this will give me two things. Evaluation of this force at the interface from one region of the flow, evaluation at the same point from another region of the flow, and that gives me two forces, and then do a balance of forces. Okay, that's the idea. That's where these nonlinear boundary conditions come from. So how am I going to do this? So here's a picture again. I think that's the best way to do it. So here's the fluid surface, right? Fluid 1, fluid 2. There's the point x0, which is for the position vector x0. The normal to the surface is given by n, and there's some force, right? There's some force there. So all I need to do is resolve this force into three principal components before I do the balance of forces. So the way I'm going to do it is to resolve forces in the normal direction. That's very natural. And then also resolve forces, take two independent vectors in a tangent plane locally to this vector, right? So I wrote it here as T1 and T2. Okay, so depending on the problem, you can choose how you define T1 and T2. The normal is very straightforward to find, right? If I think of this surface as a function of x and z, right? Y is a function of x and z, then the gradient of y minus this function is the normal, right? So that will give me the normal. And then a little bit of differential geometry will give you T1 and T2. So thinking about this now, right? What all I've done is I said there's a force that I can resolve into three directions. Now, if I go and do this force balance, that will give me three equations, right? It will give me three balance laws at each interface. Okay, and if you remember, there were two interfaces, so that's the 6 missing conditions that I was after. So here they are in a little bit more detail. So these are the conditions. So one way of doing it is you take the matrix, 3 by 3 matrix, times the vector n. Okay, that's the force. So that's a 3 by 1 matrix, and then dotted with n. That's the force in the normal direction. And then do the same thing with T1 and T2. So this will give me the normal stress balance, and this will give me 2 tangential stress balances. Now, linking up with what Darren did before, Darren also applied a tangential stress balance, right, at the interface. But it was only one direction because the flow was not 3D. Okay, so they were there, just one of them was identically satisfied. So going back to our count, this 3-layer problem with the 2 interfaces, we said we get 3 of these at each interface, so that gives me the additional 6 missing conditions. There are 18, but that's not the full story, right? Because I also have these unknown shapes that I need to work out. I need equations for those as well. And by the way, this is when you add more things, surfactants, you add another field, therefore you need to add another equation. Electric fields, the same thing. You need to add more equations. Okay, so we'll get to those in a second, for the modeling aspect at least. So what are the kinematic boundary conditions? Well, the idea is that these surfaces, they're material surfaces. They don't have mass, they don't have thickness, right? They're material surfaces, so that's how we model them. And therefore, the material derivative of y minus s1 and y minus s2, or however many you have, has to be 0. And if you work that out, right, this is the material derivative, d by dt plus u dot grad, then you end up with another 2 boundary conditions like this. And I'm just writing them all, assuming that this is a function. It's not multi-boundary. Okay, these values, these functions, S1 and S2, can be defined as y equals these functions. So these are the additional 2 equations. So if you think about it, this is quite a complicated nonlinear problem, right? Not just the fact that I have Navier-Stokes equations to deal with, which already is a serious issue, but I have all these additional nonlinear boundary conditions at moving boundaries as well. And these can they can do cusps, like Mark told us this morning. They can cusp, they can have topological changes and so forth. So incredibly rich problem. So we need to devise ways to analyze it rather than just compute it. Okay, so back to the normal stress balance and tangential stress balance. So all I talked about up to this point is, given a point on the interface, I know how to resolve it normally and tangentially, okay? But I haven't written down a balance yet. So what I need to do is take the value of this force from above and from below, and then write down an equation. So what does this mean? This means the value from region 1 minus the value from region 2. What's that equal to? Is it 0 or is it something else? So these are the conditions, right? So these are the two normal stresses. This is at S1, this is at S2, and then two conditions tangentially at S1 and also at S2. So what are these equal to? Okay, so let's begin with the tangential, with the normal stress balance first. Okay, so vertically, so I want to resolve forces in the vertical direction. Well, if there is surface tension, then I will get a jump, and this jump is proportional to the local curvature of this surface with constant of proportionality gamma, which is the coefficient of surface tension. Okay, so this may not be constant, by the way, as far as the normal stress balance is concerned, but if it's not constant, then it will come in to tangential stresses. So we'll get to that in a second. So what we know then is that the jump in the normal stress is that there will be a jump it's across the interface, and that jump will depend on the local geometry. Okay, so here's a picture, which you can write down, by the way. There's formulas for that. So here's a picture to see what that really means. So let me just do a thought experiment, and I'm even going 2D, right? It doesn't matter. Suppose everything else is gone. There's no flow, there's nothing, just interfaces, right? So if somebody comes along and shows me a picture like this and says, this is P1, this is P2, and I ask the question, which pressure is bigger? Then clearly P1 is bigger than P2, right? And so being bigger than P2 means it will push fluid from region 2. So it's the same thing with a bubble, right? If you have a bubble, the pressure inside is bigger than the pressure outside, otherwise it would collapse. So in this situation, P1 is bigger than P2. Here, however, P1 is less than P2. Okay, and this is exactly where surface tension comes in. And this picture assumes I'm just dealing with surface tension. So the jump, okay, P2 minus P1, we can easily see that that's a correct formula. I usually forget the sign. I never remember what the sign is. And I always do this little picture, right? Because I know that SXX, right, here is negative. Okay, if it's convex, it's negative. Therefore, I know exactly which sign is right. If you forget that and you go through, then your problem will be short wave, ill-posed, and you'll find out another way. Anyway. but just trying to avoid that. So if I generalize this to more dimensions than 2, then I get like full curvature there that will have the sum of the 2 principal curvatures, okay, which I can work out. So there are formulas for that. Oh, I need to do face recognition now. Okay, so the normal stress balance then will read as shown there. Okay, at the 2 interfaces, different surface tensions. What about the tangential stress balances? Well, those are additional equations, and again, if we don't have any surface tension gradients, if the surface tension is constant, then these will be 0. Okay, there's nothing to cause a drag of the flow in the absence of shear. Okay, so these will typically be 0. Now, what physical situations can we think of where this would not hold? Well, one such example would be surface tension gradients due to surfactants. Right? So if I have surfactants, then surface tension will be smaller near where the surfactant is and bigger further away. You can do the following experiment when you go home. Just take a plate, put a tiny layer of water in it, and sprinkle it with some very fine powder, I don't know, like pepper or something. Right? Just lightly sprinkle it so that it gets covered completely. And then take a tiny bit of washing up liquid in your finger and just put your finger slowly in the center. What do you think will happen? Someone ever done this, or it's just me doing this? So it will just pull out really fast, actually, right? I mean, the dynamics are really fast. And what's the reason? Well, the reason is exactly the presence of surface tension gradients, because the washing up liquid reduces the surface tension. Okay, so locally reduces the surface tension, and therefore there will be a force going outwards. Okay, it's a little bit like you take a drum and then you puncture a hole in it, right? An elastic membrane. It's the same thing. So surface tension gradients can affect flows significantly. Okay, in fact, again, I'm going to link. I mean, with Darren, we're always discussing these things, so it's really nice to be in the same room and kind of give lectures. So if you take the problems Darren was talking about with the enhancement of flow due to slippery surfaces, okay? If you put surfactants in these flows, and usually they're there anyway, they may be present. So if you put surfactants in these flows and there is a baffle, right, otherwise the liquid will be pushed out, then surfactants will build up. Okay, surfactants will, so let's suppose the flow is going this way, and here's the liquid trench that Darren showed us earlier, and it's got a baffle at the end so that this recirculates. So that means the surfactants will get pushed by the flow towards that point. They build up, and then they will create a force. Which way is that force going to go, given our little dish experiment? So there's more surfactants here, so it will be that way, right? So the force, so in fact, there will be a force that opposes the flow. So you're trying to drive the flow in one direction, but this will cause a retardation. And these are called Marangoni forces. And in fact, in these very tiny geometries, they can completely cover the whole thing with surfactant. And instead of getting a slippery surface, you get a no-slip surface. So you need to come up with ways to alleviate this. And that comes in through exactly these types of boundary conditions, as I will show you next. So here's a statement of all these physical things I mentioned. Here's an exact statement of those. It's the gradient of gamma, the surface gradient of gamma. This is the shape in 3D. Surface gradient of gamma dotted by the principal tangential vectors, T1 and T2, and those will give us forces at the interface. By the way, there's other physical situations where you can get these things without surfactants. You could have charges accumulating on a surface. If you have ionic fluids, you get charges on the interface, and in fact, you can actually drive flow with non-uniform charge distributions. Okay, there's some really nice experiments where they do this. How do they do it? Well, they do this. They take, I'll say this because I'll do a bit of electrostatics as well. So what they do is the idea is if you have a surface, there's a liquid surface, right? If I have a non-uniform voltage on this surface, it will give me a non-uniform distribution of charges. Now, how do you do, if you're a clever experimentalist, which I'm not, I would say to do a non-uniform one, I would say, oh, you put another plate there and you change the voltage along there. But that's not what a clever experimentalist would do. What they do something much simpler. They put a constant voltage on the upper plate, but slightly change it so that there's a bigger gap there than there. Therefore, the electric field is bigger there than there. So that's how you get a non-uniform field, very easily. And this will give a distribution of charges, which in turn give these types of forces. So by just sitting there with this plate slightly moved up, you can get a recirculation zone. You can drive flow. These types of experiments were done by G.I. Taylor many years ago, down the road. So, so what else? So it's what I was saying before, right? I added more physics, but I know how to deal with my equations, but that means I've added more unknowns. And what are these unknowns? Well, the unknowns in this case will be the local surfactant concentrations at the interface. Okay, it gets more complicated than that because they can also be dissolved in the liquid, and then I need to do lots of other things. But if I assume that they only live on the interface, then I have to track two more unknowns. So I need equations for gamma 1 and gamma 2, which would be the surfactant concentrations. And we call these insoluble. So let me just give you the equation. I don't expect you to follow this or where it comes from. I'll just give it to you, but it's good to see the different terms in it. So wherever there is a surfactant and wherever there's a sharp interface, I will get an equation of this type. I derived this in an Eulerian frame. That's why you get these weird terms. But I think if you want to do any analysis, it's probably better to be in an Eulerian frame. And that's where this term arises from. Then I have various effects. One effect is surface convection, because there's a velocity at the interface, so it will move surfactant around. Then there's interfacial stretching, right? When the interface stretches, the local surfactant concentration will change, and then there could be diffusion. And then you can work all of these things out using differential geometry. Okay, it's not hard to do. And like I said before, other effects. What other things can you do? or you can have electric fields, magnetic fields, thermal gradients. I mean, we've done all of these problems. These are fairly straightforward, straightforward. They're well defined. This is incredibly challenging. If you have evaporation, condensation, these are incredibly challenging problems. So we're kind of working on those a bit now. And then also soluble surfactants are quite challenging as well. So, but that's for another time. Okay, so let me kind of, instead of going to this multiphysics thing, I'll do something very simple. I'll just do the simplest possible electrohydrodynamics problem I can think of. Okay, that will give me something rich and interesting. And that's to add electrostatic effects to these types of flows. And I'll show you what the flow is in a second. So if I take the Maxwell equations and take their electrostatic limit, then I have the Faraday law, the curl of the electric field is 0, and the Gauss law that says the divergence of epsilon times the electric field, that's the permittivity of the fluid in question. The divergence of that is 0. And then if this is a constant in different regions, then E is minus the gradient of V, so V is our harmonic function, okay, in 3D. So this is in 3D. And the permittivity is epsilon. So let's move to the simplest 2D problem now. And I'll show you how we can do an analysis to get equations that describe this. So this is the simplest 2D problem. So I have a falling film, right? So suppose I have a plate at a certain angle theta to the horizontal. I have gravity acting. So the fluid will be dragged by gravity. There will be a force in that direction. Okay, that will cause flow. Then there's a shape, that's an interface that I need to determine. And then I'm going to impose an electric field as follows. I'm going to take this plate and ground it. So the voltage potential will be 0 there. And then what I want to do is put another plate here. Okay, suppose I put another plate here with another voltage potential. Then that will give me a potential difference. But the way I'm doing it, what I want to do is kind of simplify that even. I want to move this plate to infinity and let the voltage increase so that I get a uniform electric field very far away. Okay, so my boundary condition very far away will be E will go to 0 in this direction, and some constant in the normal direction. Okay, so what's the electric field problem? Well, the electric field problem will be Laplacian of V is 0, and it goes to some constant, the electric field is a constant, and since I'm doing the simplest possible problem, and this is a perfect conductor, and I grounded the plate, then the interface will also be grounded. So that's V is going to be 0 at the interface as well. Okay, so we'll use the Cauchy integral formula in a bit, because we need you'll see what we need. We need the Dirichlet-Neumann map to solve this. Okay, so that's the setup of the problem. But there's no such thing as a free lunch, right? We increase the complexity, therefore something else has to come in. And what is it that comes in to complicate things is that the stresses are now the forces, right? The local forces are no longer just hydrodynamic. They're also going to be due to the electric Maxwell stresses. But that's all very nice because we know we know that we can just, all that means I need to add another 3 by 3 matrix, or 2 by 2 in this case, I mean 2D, that looks like this. This is the Maxwell stress tensor. Okay? EI, EJ is just, EI is the component of the electric field in the I direction. So in this particular case, I have I is 1 and 2, and J is 1 and 2. So what are the boundary conditions? So here are the boundary conditions for this very simple problem. Y equals 0 is the solid surface, right? So Y equals 0, I have no slip. There it is. Then I need to bring in the normal stress balance. Here's the normal stress balance. There's only one interface now, so what I need to do is take the force, there's the force, including the electric field, and dot it with the normal direction. That will give me the force. And then I'll take the jump across that, and that's equal to gamma times the curvature. So that's what happens at the interface. Then I need to do the tangential stress balance. Okay, the tangential stress balance is written there. And what I really need to do is take the full thing and put it in there. Right? So I'm actually using a result that says that T transpose TMN, the jump is exactly 0. Okay, why is that? Well, you can work it out algebraically. That's not hard to do. But there's another reason. The reason is that there are no charges on the interface that cause any type of distribution that would then cause forces as we had in this example. Okay, so there's no local tangential force due to the electric field. There can be, by the way. It doesn't mean they're not there. It's just remember, I'm doing the simplest possible model. There are situations where this can happen. Then what else? Well, I have a kinematic condition at y equals s at the free surface that I don't know. I need to work out. That's the equation for it. The voltage is 0 at y equals s. And then the voltage will go to some specified value very far away. Okay, so that's the structure of the problem. Okay, so we can see mathematically, we can see how this would work, right? So and again, this is how I would think of it if I was doing a numerical simulation. Somebody came along and said, here are the codes, go and do it. Then what would you do? Well, you start with a given shape, right? If you know S, then you can go and solve Laplacian V equals 0 above, right? With your given code. Then you will find the stress, the electric stress tensor. Put that into 2. Okay, put that into 2. And then, well, I would solve this and then put the solution in 2. But in 2, what 2 needs is not V, it needs derivatives of V, right? So you would take V and then find the normal derivative of V to the surface. And that would go in here. Okay, and then you have boundary conditions to solve the Navier-Stokes equations. Once you solve them, you update the S, and then you go back and you keep going. Okay. So that would be the numerical scheme. But I'm not going to do this. I think we'll see how that is done later on in the week. what I want to do is take advantage of some disparity of scales in these problems to see if I can derive models that I can then analyze and get information about the flow. So typically the mean film thickness, if I call it D, is usually very small compared to the types of waves that I see forming on these interfaces, which I would call L. So typically D is about a millimeter and L is of the order of several centimeters, depending on the problem. So, so if I call delta D over L, that's a small parameter. Okay, so what can I do? How can I use this small parameter? So again, maybe I won't go through the details, but this is the dimensional problem of what I need to do, right? Navier-Stokes equations forced by gravity on this domain, minus infinity to infinity, and between 0 and S. And then I also need to solve the Laplace problem above, and then couple the two through the interfacial conditions. So if I look for a base state, right, in other words, look for a flow that doesn't depend on either x or time, and the interface therefore is flat, then I can get a solution that's like a parabolic shape. It's just a Poisson flow. It's a half Poisson flow. And then you can also get the pressure, right? You can also get the pressure directly by integrating the second equation, because now all I have is a hydrostatic pressure, so I can get that also. And little detail, in the pressure there's also an electric pressure. Okay, that just comes from the fact that I have a difference in permittivities. Okay, so there will always be a pressure due to that. But that's a constant which I can just carry. So the way I want to proceed is to write the solution as a base flow part, u bar, v bar, plus some other functions. I'm not assuming these functions are small or anything at the moment. It's just a redefinition of the dependent variables. Now, what about the boundary conditions? So here's how you would get these. If you want details of it, maybe I'll go very quickly through this. So given this shape, I can find the n and the t. Okay, so there's only these two. There's only one t. Then I go into my normal stress balance, and the normal stress balance now has fluid hydrodynamic forces on one side, right, in the liquid, no electric field forces, and only electric field forces in the air region, because there's no liquid there. Okay, if you have another liquid there, things become much more complicated, and we'll see that later. So I need to work this out, so it's just a matter of writing down the matrix and doing the multiplication. There's no clever way around this. You just have to write it down and do it. Now here's the electric field, and again, maybe I didn't say that on the previous slide. I can again write it as an exact solution plus a disturbance. Okay, and this takes into account the condition at infinity. Therefore, it's enough to assume that that goes to 0, very far away. Okay, and then this is what you would do to get the other part in the normal stress balance due to the electric field. Again, you write down the matrix, left multiply, right multiply, and work it all out. So some horrible nonlinear equations will result. Okay, so I'll leave this. But by the way, I'll give all these notes to Mark, and he will send everything to you if you want them, so I can skip a few things. So this is just getting some of the constants that play no role whatsoever. Now, the normal stress balance and the tangential stress balances can be written into these equations. Okay, so what's involved here? Let's look at it a bit. So this is the pressure in the fluid. This is the viscous stress part. I'll tell you in a second where that comes from. This is surface tension. This is the effect of the electric field. Okay, so in order to solve the fluid part, I need the electric field. And as we saw before, it's kind of like the Dirichlet-Norman map, right? I have V is 0, but now I need the normal derivative of V to come in. This is the tangential stress balance. Right? So this is the other condition. And just some details in deriving this. I just used some identities. It's really not important, right? I mean, you can leave them as they are. It's not important to do that. So let's now non-dimensionalize and see what we can do asymptotically. So let me non-dimensionalize. There's a natural scale for velocities because I have gravity driving things, right? So this is a good velocity scale. Time is then going to be d over u, right? So u0 is given here. D is the only other scale I have, really, right? And then I can non-dimensionalize voltages with E0 times d. Now, if you had a finite distance far away, you could use that, but most of the action happens locally near the interface. So d is a good parameter to non-dimensionalize by. Once I do that, I end up with some dimensionless numbers. These are the Reynolds number, a capillary number, and then an electric parameter that measures the strength of the electric field. So this come out naturally, and we will see them in the dimensionless equations, which are given here. R is the Reynolds number, so this is the x momentum, y momentum, continuity of mass, and this is the electric field. So this is the problem. The boundary conditions are V equals 0 at the interface, right? All of these are at the interface. V equals 0, kinematic, tangential stress, normal stress, and then 0 slip at the wall. So in general, you have to do this problem fully numerically in general, okay? And what I want to do next is see what happens in a situation when the film is thin compared to the wavelengths of the waves that form, to get some idea of the nonlinear dynamics involved. Okay, so I want to kind of proceed for that situation. So let's try and set up the asymptotic problem. Okay, now what I did is I chose to non-dimensionalize everything with the thickness. So the scale in the vertical direction is of order 1. Okay, because I chose that thickness to be my length scale. And however, right, whatever happens here, here I have an electric field that needs a boundary condition very far away. Okay, so I cannot get away from the fact that if the waves are long, right, then I will get a very long wave for the fluid dynamics. But in the outer region, okay, if the waves are very long, then I need to go as far away vertically in order to satisfy my boundary conditions. So necessarily, whatever happens that simplifies the flow in the liquid film, right, due to slenderness and all these things, that will not hold in the electric field. So I always get a coupling of something that I can analyze, maybe by hand, as we will see, and something that will always be elliptic, an elliptic problem. The situation is much worse if this is a liquid and this is another liquid, because then you have to deal with the Navier-Stokes equations up there. But that's also doable, and we will see that later on. So it's just a matter of taste, how you do this. But the appropriate length scale then in the x direction is 1 over delta, if delta is the small parameter. Right? Delta was d over L, remember? So 1 over delta is L over d. So 1 over delta is exactly the dimensionless wavelength. So there's no magic in that. That just comes up naturally. You could, of course, make this 1, and this epsilon, and this 1. Okay? But that doesn't matter. It's the same. So that's the idea. So in the liquid film, okay, in the liquid film, I need to take the Navier-Stokes equations, state the full equations of motion, change variables, right, so that x is big X over delta, right, because I need a stretched variable. Keep y of order 1, so that wherever I see d by dx, I'll pick a delta d by d big X. And that's, mathematically, that's where the simplifications come, because these Laplace type operators localize to just vertical derivatives. Okay, so that's really the big mathematical simplification. In the outer region, however, I don't have this luxury. I have to keep x and y both. I need to introduce also y to be 1 over delta, big Y, and then I need to address elliptic fields there. Okay, so that's what happens. So let me talk about the electric field problem first before we get to the fluid mechanics problem. So as we said before, I'm going to write V as V bar plus V tilde, where V bar is the exact solution for a flat interface. It's just 1 minus y. Okay, so there it is, 1 minus y. I can just derive it very easily, right? Because there's no variation in x, so it's just V bar y is 0. And then applying the boundary conditions, I just get V bar is 1 minus y. Then what's the electric field problem then? Well, the electric field problem, the Laplace operator doesn't change, right? The derivatives there are with respect to big X, big Y now. The interesting aspect now is that, of course, the gradient goes to 0 far away, because I took that out. But now, instead of having V 0, now I have V is S minus 1. So it's the shape minus 1. So it's a Dirichlet problem. Okay, if I know the shape, I can then go and solve this problem. Okay, so that's the exact formulation. So what I said before was not right. Let me go back. So yeah, here I'm just doing the exact problem. I haven't done the rescalings yet, right, with delta. So this is the exact problem. Now I want to rescale. Okay, so if I rescale, then to big X, big Y, of course the Laplace equation doesn't change. This boundary condition also won't change, but now I have to apply this at y equals big Y over delta equals to S. Okay, because I've gone from Y to big Y over delta. So what's the boundary condition in terms of big Y? Well, it's delta times S. So that means, as far as the outer flow is concerned, this interfacial condition that says Y is equal to S minus 1 or whatever, at Y equals delta times S, it's as if it's at 0. Okay, to leading order of the expansion, I can impose this boundary condition of big Y equals 0. Okay, I don't need to impose it there because delta is small and I'm seeking a leading order solution. So it's enough to go there. So what's the lesson for this? And this, by the way, happens in all these types of problems, whether you're doing evaporation or whatever. The lesson is that if you have elliptic problems with Navier-Stokes problems and one of them is thin, then all this information that you get from the lower region will be seen for the outer elliptic problem on a square domain or rectangular domain. Okay, the bottom boundary will trivialize to Y equals 0. And that's a huge help, right? Both numerically as well as analytically, as we will see. Okay. So now I have a very well-defined, self-contained problem for V, right? If I know S, if I know S, I can solve this by using Cauchy's theorem. Exactly how Darren told us how to do it. In fact, Darren can probably find 10 other ways of getting this as well. But what it really does, what I really need is a Dirichlet-Neumann map, right? I know the Dirichlet condition, and then I need to find this. It's quite easy to show that it's minus the Hilbert transform of Sx. Okay, so you either use Cauchy's theorem or you can do it with Fourier transforms. It really doesn't matter. Okay, if things are much more complicated, the Fourier transform will also give you this. And this is the definition of a Hilbert transform that I'm using. So what does this condition become? Okay, I had a coupling between electric fields, fluid problems through this boundary condition, but now I have managed to find V in terms of S, right? So this is really a function of S. So my fluids problem closes now, if you like. Okay, so but that's the fully nonlinear version. I need to think about what happens for small delta. So after we do the transformation, right, as we said, we scale variables with respect to 1 over delta y and 1 over delta big X. And then d by dy will pick a delta there and so on. Right, so there's some simplification to be found from here. So if I do this carefully, right, if I expand this quadratic, the constant terms cancel, of course. That's by design, by picking the constant so that it gives me the correct solution when things are flat, and then I'll just pick up a minus 2 delta v tilde y from here, right? That's the order delta term. But v tilde y is the Hilbert transform of S, x. So I know exactly, so the problem will close. Okay, and that's shown here. Okay, so, and then of course, depending on what the capillary number is and so on, I can always choose WE to bring this effect in. So in doing these problems, we always insist right? We do all these asymptotics with deltas and epsilons and all that. And then we insist in keeping physical effects. Okay, so if I want to keep electric fields, I need to pick the Weber number so that it stays. Okay, so it's quite straightforward then, in this particular simple case, to proceed with the fluids problem without the electric field, and then I can just come and put it back in. Okay, but we'll see that as we go along. Okay, I think this ran out now, so I need to go here. How are we doing with time?
About 16 minutes.
Okay. All right, so let's see. Let me see how. By the way, I wrote all this stuff out. I had to redo a lot of things actually, and I'll show you a new type of solution. Hopefully. So now I want to deal with the fluids problem, right? I said what the electric field would do. Let's now deal with the fluids problem. Here again are the Navier-Stokes equation. We've seen all that before. Here's my base flow, non-dimensionalized, this half Poiseuille flow again. And here are the full equations after I write everything as deviations from the base flow. Okay, nonlinear deviations from the base flow. So these are the new equations. Okay, nothing in that really. And these are the boundary conditions at y equals s. So let me just show them again. So these are the boundary conditions at y equals s: kinematic, tangential, normal. Okay? So these are the three conditions, including no slip. Okay, so what do I do next? Well, let me do exactly what I did for the electric field, but now I'm working in this thin layer, right, that is very long, right, 1 over delta times big X, but it's of order 1. So here's a picture, right, order 1 over delta. And then what I need to do is do an expansion in powers of delta, okay? This says it follows from F8. I don't even know what F8 is. Oh yeah, okay, I know what I mean by that. So what do I mean by that? This expansion everyone is okay with, right? So you have a field, we've got a small parameter, so it's U0 plus delta U1, and so on. But then the V is delta V0 plus delta squared V1, and so on. Well, the reason for that is because if I start with this equation and do my change of variables, right, introduce the stretched variable, this term becomes this, delta times that V tilde y is 0. So necessarily this has to be of order delta. Okay, otherwise I won't get the balance there. I'll just get Vy 0, therefore V 0, it's just all trivial, right? So I need to start my expansion for V with delta. Okay, so once I do that, then So by the way, when you do asymptotics, if you don't know what you should do, expand everything inside. Okay, you just expand everything. So that's what I'm doing. I'm expanding those. I'm also expanding the interface. Okay, it's also S0 plus small correction, and so on. If you didn't need to expand, the equations will tell you. Okay, so let's expand everything. Then, so I'm going to try and go through this in a systematic way because I think in this field it's very unfortunate because when you go and read papers, you start reading through it. Here's the Navier-Stokes equations. Oh, here are the expansions, and it's delta to the 1/17th times something, and so on. And you never know, and then you're just doing algebra, right? So it's much better to just do it from first principles. So this is what I want to try and do. Now, the pressure, I don't know what it is. I'm just going to call it delta P. Some delta P, I don't know what the value is, times P0 tilde, and then of course the expansion in delta proceeds in the usual way. So delta P is to be found, and it will be controlled by the physics, as we will see. Okay, so how do I determine delta P? So the way I can determine it is to go to the normal stress balance, which is here. There's the normal stress balance. Okay, equation F11. And let me substitute all these changes of variables plus expansions in that. And just carefully pick out what's important. So if I do that, this is the equation I get. Okay, so this first term clearly is going to be irrelevant. Okay, then I've got the gravity term. This is gravity pushing fluid down the slope. Then I have my delta P, but I didn't know what it was, so there it is. And then I have the surface tension term. This has now picked up a delta squared. The reason is that I'm really long, right? And my little x is 1 over delta big X. So that picks a delta squared because I have two derivatives. Okay, so this is kind of written in an exact form. But really what happens if you look at things, this is irrelevant, right? So really if I want to keep surface tension, if I want to keep this term, then the balance between this term and delta P, or the relative balance, the relative ordering between these terms, will give me different physics. Okay, and that's what we're going to try and do. C is what's called the capillary number, and C very small means the surface tension is very big. Okay, the gamma is in the denominator. Yes.
When you said assume that S is order 1, is that actually from the kinematic condition?
That's from thinking of what I want to solve if I have the undisturbed flow like this, with this being order 1, right? Then what I want to do, what I want to say, I'm going to allow, I can allow perturbations of small sizes, really small sizes, or sizes as big as the thickness. Okay, so by assuming S is S0 plus delta S1 ... where this is order 1, I'm assuming that it's as big as the undisturbed thickness, and it can actually touch if it wants.
But if you assumed it was smaller, you could still find a physical effect.
Yes.
You could see something different.
You can. You will see things with much weaker nonlinearity. But we'll get there. I'll do that. I mean, I'll show you how this is normally done in expansions in delta, but you can also do it in one shot using multiple scales. And that's also a new thing I want to show. But for the moment, that's a very good question. For the moment, I assume it's order 1. Okay, so the only thing that saves me is that it's really long. It's order 1, but really long. Okay. And of course, if it shocks, then that assumption is gone. So we'll see. So let's go back here and do some estimates for the delta p. Well, there's really two canonical cases here. Is if delta p is of order 1, okay, if delta p, because I'm assuming the Reynolds number is order 1. Reynolds numbers are 10, 20 values like that. They're not much bigger than that. So if surface tension is small, but not too small, right, delta squared, we'd say, surface tension is delta squared, then this gives me an order 1 value for the surface tension. That will drive a pressure with a delta P of order 1. Okay, so in other words, P0 will also be order 1. So that's the balance. It will give me this balance between surface tension and gravity as well. So this brings surface tension, pressure, as well as gravity. So you can think of this differently, right? Suppose I want gravity to appear. Then this will force both that and that to be 1, to be of order 1. So that gives me C is delta squared, delta P is 1. However, you can assume gravity is really strong as well. Surface tension is really strong. In this case, delta Q, capital number is delta Q. So if I look at this, right, then this says that this term is 1 over delta. So it's a big surface tension force that can, of course, be balanced by pressure. So the pressure will be a 1 over delta. So this is a situation where the perturbation pressure, the surface tension is so large that when there's a disturbance, it causes a pressure that's much bigger than hydrostatic. Okay, so you need surface tension to be really big. Then delta P is 1 over delta, and then gravity is completely irrelevant in this case. Okay, it's a next order effect. Okay, this case 2 is very easy. You can do it directly. Case 1 is much more complicated. So let's do case 2 first. Okay, so this is what happens if I now take my Navier-Stokes equation and put all these scalings in, right? So I'm writing everything in full form. There's my delta P, so I can use this for any of the two different situations. Now this is where things get saved. This term is going to disappear in the first couple of orders, right? So I'm only going to get ddys. So u0xx is going to have a delta squared, and then I expand the u0yy, delta u1 yy, and so on. Then the second equation, if I look at the second equation, again, we're small relative to the wavelength, then the dominant term is really this. Okay, remember delta P was either 1 or 1 over delta. So the dominant term is P0Y0. This is what happens in lubrication approximations. The pressure is just hydrostatic. Okay, so that means, again, this is great because it means if I can find P from the surface tension, then it's the same everywhere in the flow. And I can just use it. And then this is how the continuity equation will expand. Okay, so let's do the very strong surface tension first. So this is the easy problem. So delta P is 1 over delta, and then immediately, remember from my normal stress condition, the only balance was, okay, the only balance will be this equals that. Okay, so I know exactly what P0 is. So R Reynolds times P0 will be 1 over C bar, where C is delta cubed C bar, right? It's just a parameter. We can take it to be 1, we just keep it there in case we want to switch it off. And then the Navier-Stokes equations are really simple. Okay, so this is what happens. I just get u e to u 0 dy squared is some function that involves S0, right? So I can integrate that immediately. And P0 y0. Okay, we said that also. So let me integrate. I get two unknowns, A and B. And B is 0 because I have no slip at y equals 0. So that's gone, right? So there's only one unknown function I need to find, and that's A. Now, how do I determine A? And again, this is what happens in these problems. You have to use all the boundary conditions available to you. I've already used the normal stress condition. Now I need to use the tangential stress condition to determine A. So where does that come from? So again, take the full, so you have to do this carefully, take the full nonlinear tangential stress condition and introduce all your scalars. Okay, so let's take any one of the variables, right? There's a u bar plus u0 plus delta u1, y, and so on. But they're all evaluated at S0 plus delta S1 and so on, right? So you can tailor expand all these things and collect terms, order by order. So if I do that, then immediately I'm going to get an equation that tells me what the shear is at the interface of the perturbation velocity. Right? So the shear of the perturbation velocity is equal to something involving the free surface. Okay. And therefore, this boundary condition will determine A exactly, and it's given here. Okay, so what do I have? Well, what I've got up to now, I've got U0 completely in terms of S0. Okay, because I've determined A in terms of S0. So the only thing left to do to get a partial differential equation that will tell me what the evolution of this shape is to go to the kinematic boundary condition and do the same thing. Right? Again, expand everything in sight. So there will be the delta V0 and so on. Then there's an S0t, delta S1t, and so on. Then there's this term, right? All these things. Okay, so where do things start get interesting? Well, this is an Sx, therefore I pick a delta there, right? Because d by d little x is delta d by d big X, right? You remember this? It was the same reason that we got the delta showing up here. So, so whatever happens here, this term is order delta, this term is order delta, and then I have this. Okay, so what happens then? What does that tell me? I'm just trying to be interactive. What do I need to do to bring unsteadiness in? Because, by the way, this you can now, let me say it more mathematically. If this term is not there, right? If this term is not there, then what I will get is kind of an identity, if you like, of things that I already determined. So it's kind of overdetermined. The problem is overdetermined. So what I need to do is just like I introduced a very long wavelength, I can introduce a very long time scale. Okay, so in fact, you can see that if I take, so I had a t, right? T was my initial variable. So if I introduce a new time scale, t1 over delta, what does that say? Where t1 is order 1. Okay, what does that say? Well, it says since delta is really small, t, the actual physical t, is very long. Okay, so the price you pay for making the film really long and really thin is that you have to wait a very long time to see things. If I went to order 1 and epsilon, then it wouldn't be that. Okay, so whatever happens, I need to bring that term back in. So this should go to that. Okay, so d by dt will pick up a delta. Sure, yeah, let me just get the final equation. Yeah, let me just get to S. So, okay, so that's what I've done there. So order delta will then give me a closed form equation, really, if I can find V0. Okay, but V0 I can get from this equation. Okay, because this will be U0x plus V0y is 0. U0x is a polynomial in y. I can integrate it and all these things. So let me show the final equation. I'll skip the details. I'll show you the final equation. So this is the final equation that you get. A PDE, right? So what is it? It's a PDE, fourth order in space with a good sign. This is due to the pressure gradient. Right? It's from the du dy was equal to something, right? That tangential stress. That's where that term comes from. And now I've brought in the electric field again. Okay, I can just bring it and put it in because I've already worked it out, and it comes in as a kind of deviation from the pressure. So this is the equation we get. So one last thing. Now this are quite horrible equations, right? Because they're degenerate nonlinear parabolic equations. This thing can go to 0. I've assumed it can be as big as order 1. So when this goes to 0, you get a singularity in the equations. Now, what's interesting is that you get some really nice phenomena, even for this very trivial problem, a very simple problem. So if I don't have an electric field and I have these two terms only, then everything is stable, right? There's no instability. But if I include the electric field, then I get dispersion relations that look like this. Right? If I look for waves of the form linear disturbances with the form e to the ikx plus sigma t1, then the real part of sigma is equal to that, just from the properties of the Hilbert transform. So this term will destabilize things. Okay, so you can introduce unstable waves. Okay, so I should stop there and we'll continue.
Yeah,
Yeah.
let's take a break. So
Okay.
let's take a 20-minute break. Come back at 1:45. Okay, there should be coffee outside again.
Okay.
Lovely stuff. Are you an expert on Dirichlet norm in maths, or do you know much about it? I don't look. Okay.
Darren probably knows more.
Okay, yeah. Maybe it's like I'd speak to you about a problem which I'm having, like expanding the asymptotic
Yeah.
in the free surface. I don't know if you've ever done that.
So you set it up as non-linear and then expand in it?
Yeah. So it's a waterway. It's not this problem. It's the water. But it's all the Class's equation.
It's like the tsunami.
Yes. I was just wondering if you do. You know.
Yeah.
Yeah. Because it takes the free surface is obviously an unknown.
Yeah.
And if you change the free surface, you're changing the domain. And because you mentioned it, it's like, not many people know that they're comfortable talking about it. You know,
yeah, I thought it was easier to do it in Fourier space.
Yeah.
It took about 1 minute.
Yeah, you're right. You do. Yeah, we did in the paper that came out in Siam. Yes. You expand. You think of it as an operator. You expand the operator.
Exactly. I'm happy expanding it in terms of the potential, the argument. But you've got this. It depends on the non-linearity on the free surface, doesn't it? Regardless of the problem, if the free surface is changing, it depends on the shape of the free surface. So you can expand it, and then can you expand the free surface as an asymptotic expansion within that?
I don't think so, because the domain is changing.
The domain is changing, exactly. Yeah.
No, I think what you do is you think of it as an abstract operator and expand the operator.
Yeah, exactly. If in the argument of the potential or the velocity or whatever, whatever's in the bulk quantity rather than
the shape.
Yeah. Okay, that's what I was thinking.
Then I guess it's all. Then it comes order by order. I'll look and see exactly how we did it.
Yeah, no, I mean, there's not many people. I'm learning about it. And it's
Maybe Shin may know.
Okay.
Shin's
on Mark's or
I don't know if he's used that.
So I know you can expand the potential. I was just wondering. Anyway, it's because you mentioned Dirichlet norm in maths.
Okay. Very simple.
Yeah, sure.
Is it worth stopping the recording for 20 minutes?
Okay, so I try and do that. It's got my face to start with, yeah.
Okay. Okay, Sarah said I could start, so I'll start. Okay, so let me continue a little bit with this. So this is the type of equation we get. But let me show you another equation that comes up in a very similar kind of situation. But now I'm not even going to tilt the plate. So gravity is directly pointing down, and therefore this is always stabilizing. Gravity will always be stabilizing in a situation like this. So the only hope to make things unstable is to introduce an electric field. So if you do that, this is the type of equation you get. Exactly the same type of analysis, where G is the sign of gravity. Now, what do I mean by that? G is actually 1 if the fluid is above, right? The fluid is lying above, it's 1, and it's -1 if it's below. Okay, so if the fluid is underlying, then it's -1. So it would be destabilizing if this is -1. So this would be Rayleigh-Taylor instability, right? A heavy fluid into a lighter fluid. So let's consider all of those, right? All of those situations. So we saw that if, well, first of all, if G is less than 0, so this will add to instability, so it would even be unstable without an electric field. But if G is greater than 0, then we get new phenomena. These are called Turing instabilities. This was first seen by Alan Turing in describing pattern formation. And these are kind of monochromatic instabilities. So what do I mean by that? So now let's do G is greater than 0. So the fluid is above and gravity is stabilizing. And I can write down the dispersion relation as before. Okay. And this is the dispersion relation. There's a k squared times this quadratic polynomial. Now, this is surface tension, so there's a minus, always stabilizing. This is the electric field. There's a k cubed. It's actually k squared absolute k, but for positive k, it's k cubed. That's always destabilizing. And then there's a k squared times minus g, so this could be stabilizing if I have the fluid lying above. So, depending on what this value is, or in other words, depending on how strong or how weak the electric field is, I can get different effects. So, let's start with a weak electric field. So, in other words, this is less than 0. G is positive, so this is less than 0. So I get 2 zeros there, and then everything is stable. I get a picture like that. If I have a critical value, an exactly critical value of the electric field, then this hump there starts moving upwards, and in fact it gives another neutral stability point at a finite wave number. So 2 zeros there, another 2 zeros there, fourth order dispersion relation, right? But then if I'm above that critical, then I get a finite band of unstable waves. And this is exactly pattern formation, right? If I was doing an experiment and I was turning the electric field up, then what I would see is everything is stable, and then at a certain value, immediately you'll get patterns forming, which you would never see with a long wave unstable problem, right? If the dispersion relation was like this, you would never see that. Okay, so Turing instabilities are really quite interesting. Now, okay, let me tell you a little bit what more we can do mathematically, and also an open problem for anyone who wants to try it. I tried it and couldn't do it. So this is the form of the equation that we have, right? So there's some linear operator. Okay, some linear operator times some nonlinearity, something like this. Okay, so what we managed to do, is to show that this has smooth solutions if you start with smooth initial conditions. Okay, in fact, as long as the initial conditions are in H1, in other words, their derivatives are bounded, then you get existence of solutions, and they remain bounded with bounded derivatives, okay, for all times. It doesn't mean that the solution will not touch down in finite time or infinite time, and that's something that's hard to prove. But what you can prove is if you also assume that the second derivative is bounded, then it will touch down at infinite time. Okay, so you can actually do all that using Lyapunov functions and estimates of the energy functional. Now, physically, what's all that? I mean, that's, you know, you do dynamics of this. If you do dynamics of this to see the touchdown, you may have to integrate to times of the order of 10 to the 6, 10 to the 8, and it still doesn't touch down. It gets thinner and thinner and thinner. So usually it means we've neglected some physics that will come in, and really the physics we've neglected are Van der Waals attractive interactions that would give you touchdown in finite time. Okay, in fact the touchdown is locally with cusps within this formulation and probably corners in the full problem. Okay, so that's what happens for this very strong surface tension case. Yeah.
So the fractional singularity is in direction H double prime or H prime?
H.
H will be 0.
Yes, H tending to 0 is what we call a touchdown singularity. Right, so it thins to 0.
Singularity.
Oh, well, because if it touches down, then the equations are not valid when S0 is 0.
Because of H double prime.
H double prime could be finite. I mean, it won't touch down, it does asymptotic, unless you do something else.
Which term is singular?
I think the best way to think of these is if you look at the equation, which is not here. If you look at the equation, right? If I look at this equation, if this goes to 0, right? If this term goes to 0, that's my highest derivative is h cubed times 4 derivatives, right? So if that goes to 0, you're losing, it's a singular problem. So you'll have to get weak solutions that then dewett and all these things. Okay, but doing it for a situation where instead of this type of equation, doing it for this equation, we can't really use the Lyapunov technology to do this, because it's not of that form. You need to integrate things twice in order to use that. So I don't know how you do that yet. Okay, so this was the easy case, right? The C capillary number very small. But now let's go to a case where it's small but not as small. Okay, so now I'm going to go to a situation where the capillary number is delta squared. So I want to add more physics. The physics I'm adding are gravity, right? So this type of term, as well as inertia. We'll see how inertia comes in. So in a case like this, as we saw previously, where I was working out the delta P, if the capillary number is delta squared, then the surface tension term was order 1. It was delta squared over capillary S double prime something. So that means the delta P is order 1, and then my normal stress balance will give me this condition. So what's new now? Well, this term is the new term, right? I have gravity in there as well, and therefore I will get inertia. Okay, so let's do the same thing as we did before. Okay, so all I'm doing is a again, I'm going to do this slow time scale. Okay, and we'll see why I have to do that again. Okay, now something different happens, right? Before, if you remember before in the Navier-Stokes equations, which are written here, this term was promoted, right? It was a 1 over delta. So that term was promoted to balance that. And therefore you got kind of a Poisson type flow. But now I no longer get that. So the biggest term in the equation is u double prime is 0. Uyy is 0, which means I can integrate twice. Okay, I can integrate twice, ay plus b. B has to be 0 because of no slip. And then if I go back to the tangential stress balance equation, right, where I have the u bar y and the uy balancing together, then I can solve and get A exactly into this. So I can write down my solution. So this is my solution. For u0, then use continuity to get v0, right? Because v0y is minus u0x. Okay? And therefore I integrate again, use no slip, I get that. Okay, what does that mean? Well, now I need to go to the kinematic boundary condition. Again, as we had before, make the time scale change, so I get this. So to leading order, right, at order delta, I get this equation. Okay, I get this equation. I can combine the nonlinear terms into a flux term. Right? All of these equations, by the way, it's not accidental that it's always d by dt plus some horrible thing, d by dx of it. Okay, that's not an accident. That's just conservation of mass. They're always going to be that. So this is what I get to leading order. So what's wrong with this? Okay, it looks nice and simple, but it's bad news in the following sense, in that if I give an initial condition and run this, okay, a periodic initial condition, let's say. Suppose I give myself a periodic smooth initial condition where I'll have both concave and convex regions in the initial condition. Then this will form a finite time singularity in the first derivative, right? D by dx will become infinite. You can solve that using characteristics. It's very, very simple. What does that mean? Well, it means that my initial assumption that this wave was very long compared to its height, right? My d by dx is delta d by d big X. Delta is small, but d by d big X is going to infinity. So those two, that breaks down that assumption. Okay, so that means I cannot use this solution. So what do? Well, the next thing I can do is try and regularize this equation by going to the next order. Okay? I don't like that. I actually don't like doing that, but let's do it. Let's do it and see what we get. And I'll tell you.
Just ignore that one.
Sorry?
No, it's wrong. You just ignore that one.
This one? No, this will still be there to leading order. Right?
But it doesn't work.
Right, so what I want to do, yeah, I mean, that's a good question. So let me go back. Let me go back to first year undergraduate. Suppose I have that, right? Then again, this will, if I start with periodic and it's smooth periodic initial conditions, right, like this, then it will eventually, well, it's not going to increase. It has to be has to maintain the max min, right? So it will give a shock in finite time. So if I go to the next order and I put an epsilon uxx there, then this is now absolutely fine. So the idea, so this is the idea. So what did I do? I said S is S0 plus delta S1 plus dot dot dot, and I found the equation for S0. Okay, now what I want to do is find the equation for S1, because I'm expanding everything in sight, right? Anything else is kind of iffy. You have to expand everything and see what you get. So I'm going to find an equation for S1 and see if I can combine these two equations for a new variable which is equal to S0 plus delta S1.
So you will still use this?
Oh, yes.
Yeah. Okay.
Yes.
That was why I was getting confused.
Of course. I will use it.
So it's coming back in once you've added a bit to S.
Right. Once I find S1, I want to combine them in that combination.
Yeah.
S0 plus
So you're
delta
just getting
S1.
a different scaling for S, basically. You want like a different scaling for the...
It's not this different scaling. I'm just adding a little bit to it.
But
That
say
will
that epsilon comes out as like delta and a half.
Oh, forget this. that was just an aside example.
I'll just wait and see.
Yeah, wait and see. Okay, so let's go. Okay, so this is this is the strategy. Calculate one more term, and then hopefully that will regularize. Okay. Now the hopefully is a big hope, as we will see. So I found this 0. So now, so I'm just writing down what I just said. I want to find the PD for S1 and then combine the two PDs. Okay, so that's, and make sure that the combination is correct to order delta squared. Okay, so let's go to the next order. So the next order is, you remember the Navier-Stokes? Shall I write them down again? It's what we had before, right? So the U1 YY was the delta term, and then equals a bunch of stuff that I know from U0 V0. And here's the right-hand side. Okay? So the right-hand side is known. It's a polynomial of degree 3 in Y. So I can integrate. So this is the strategy. Integrate F2. What's F2? I guess you should say F21. So integrate this, right? And then I can get it, introduce two new constants, A1, Y plus B1, but this is 0 because there's no slip on the wall. And then the next stage is I have to use a tangential stress balance to determine A1. Yeah.
Why is it degree 4 if you discovered it? Would it not be 5? You had a polynomial of degree 3.
Oh yeah, you're probably right.
Okay.
It's degree 5, yes. Yeah, you're right, it's degree 5. Before it gets sent back to you. Yes, it's degree 5. In fact, the last equation, the final equation will have s to the power 6, as we will see. So I go to the tangential stress balance and go to the next order, right? Again, Taylor expand everything carefully. There's no shortcuts. You just have to do it carefully and pick the right terms. Now, this term is 0, okay, because we found it was just linear in Y. So every time you have a 0 shear condition, you get this streaming type term. So that bit is 0. So is that. No, that is probably not 0. Yeah, that's not 0 because it's a quadratic polynomial, right? The base flow. So that gives me a condition to find A1. Okay, so I can determine A1 in terms of what? In terms of S0 and S1. So I get that, right? So then I need to go to the kinematic boundary condition, but go to the next order again. So let's write that down and see what it looks like. Okay, so this is the kinematic boundary condition, keeping a few more terms, right? So this is the V. This is the V expanded. This is the ds dt. So there's a ds0 dt1 plus delta ds1 dt1 and so on. This is the u bar expanded. Again, Taylor expanded. So that will bring an S1, u0 in that term, and then the ds dx. So what I need to do is pull out of this the delta squared term. I already used the delta term. So the delta squared term will give me an equation for S1. Okay, and this is the equation here. Okay, so it gives me an equation for S1, ds1 dt1, involving all these various things, which in principle I know in terms of S0 and S1. Okay, so suppose I do that. I can get V1, right? I can get V1 immediately from here. This should say 6, right? V1 should be a polynomial of degree 6. And then when I substitute into the equation, I know everything, right? So I substitute into the equation, I get this equation for S1. Okay? So what do I need to do? I need to solve this along with this. What was it? Was there a 2 there? I can't remember. 2/3. Right? I need to solve this and this. I can think of this as a coupled system, right? But that's not going to help me very much because this will go singular anyway, right? At the finite time. So I'll be forcing something singular. So the idea is to renormalize the problem. So in other words, what I'm going to do is take this equation plus delta times this equation and try and call this thing, it's right here. Let me define H to be S0 plus delta S1, and I forget everything else. Okay, so lots of assumptions going on. So I write that and try and get a single equation for H, if I can. Okay, so how am I going to do that? So I'll do exactly what I said there. This plus delta that, and gives me this equation here. Okay, gives me this equation here. And in a sense, we've got a bit of a problem, right? In the following sense. These terms, right? These terms involve S0. All of this one and this one involve S0 only. So if I replace S0 by H minus delta S1, then, so if I replace S0 by H, in fact, then the error I'm making is delta squared. You want to see that? So that's good. But if I replace S0 by H minus delta S1 there, then the error I'm making is order delta. So that's inconsistent unless some things cancel out. right? So the error I make from there should cancel this out. Okay, so if I do that, so here's some more detail. I mean, I don't know, there's probably better ways of doing it, but all you need to do is take those two terms, right, the 2/3 S0 cubed pdx plus the delta term, right, take these two terms and just substitute in the h. And then you can show, in fact, you can show that it's exactly this plus order delta squared. So you can move everything to order delta squared and you get a single equation in h. And this is it, there. This is the single equation in h. So, and then I'll tell you what I don't like about it. So, here's my original terms, and this is all the other features, which is really quite nice, right? Because I've got inertia coming in. In fact, not only do I have inertia, but this also agrees with the transition in the hydrodynamic stability of a falling film at the critical Reynolds number. So it captures that as well. Then I have surface tension and an electric field if I want to keep it. Okay, so what's not nice about this? Well, there's two things. First of all, you've got an equation that has a small parameter that I don't know its value. It's supposed to be small, right? So it's a regularization. So it's not a parameter-free equation. So it's not canonical in that sense. You could use it as a model, of course, and I did too. We did many times, right? So we do use it as a model. Well, that's one concern. The second concern is kind of a bit more serious, possibly, is that there is no global existence of solutions for this. So in fact, the solutions can blow up in finite time. Okay, so that equation I showed you up here has this singular type structure. Has everyone seen how you get this type of behavior? I can do it in like 2 lines actually. So let me just do it.
If you've solved for H, if you find that, can you back out what S naught is? Or is
But I don't know it as 1, right?
Yeah, is that the point? Because that's what I was confused with. So, because if you could, then wouldn't that contradict the issue you've got at leading order? So is the idea that you've grouped them together that you can back the two out
Yes,
individually?
exactly.
Yes. Okay, right. I see.
Yeah. It's kind of a more non-local regularization.
So you don't know what's happening at leading order or the first correction independently.
That's
you have
right.
the
You
collective.
have to put them together.
Yeah. Okay.
Yeah. Yeah. So typically what you do is you rescale this and take delta to be 1 and then just solve it on different domains. Okay, so and it's a well-behaved equation unless you push parameters and in cases like that you can get singular behavior. So let me just show you very quickly how you analyze singular behavior. I mean, what does it mean? It means that as t tends to ts some finite time, things blow up, right? So the h becomes very big, it will blow up. So how do I get that behavior? So as t tends to ts, the h gets very big, but also the x dependence gets very small as well. So there's a self-similar type solution where things go on very short space scales and very short time scales away from the singularity, but the two are related. How do I get the relationship? Well, the way I get it is if I go to this equation, and I'll just write it down, I guess. Okay, you can see that, right? So if I go to this equation, as t tends to ts minus t from above, right? Then d by dt, does everyone agree, will look like this? That's more or less what it will look like. So if I go to this equation, and then also, I will assume that the singularity will happen at the point x equals xs, but let me assume that's at x equals 0, doesn't matter, with translation invariance, right? So suppose it's at x equals x0, then d by dx, big X, will look like 1 over x, where x is very small. Okay, that's it. Once you have that, you've got everything. You go to this equation and ask yourself, what's the biggest term available? Well, I have to keep unsteady. So the unsteady term, that should be T1, right? The unsteady term looks like H over T minus Ts. And now let's look at all the other terms, right? I mean, the other terms, can everyone see that this will win over that, and that, and that? The reason is that it's got 4 derivatives, right? It would be 1 over x to the 4. So that will definitely win. So the only other possibility that can come into the mix is then h to the power 4 over absolute x to the power 4. Okay, that's here, this one. But then, I don't know what h is, right? H is also growing very big. So this term is then bigger also than everything else, or as big as everything else. So the other term that will come in is, and I'm ignoring the deltas and all these things, h to the power 7, h to the power 7 over absolute x squared. Okay? So what do I have? 3 equations, right? So I can put this equal to that, 3 balances, and put this equal to that, and that equal to that. So I've got 2 equations and 2 unknowns. What are the unknowns? H and absolute x. And I can solve in terms of Ts minus T. So if I do that, right? So if I do that, that's exactly what I was showing there. Okay, so exactly what we do there. So everything else is smaller in this singular asymptotic limit, and if you do all that, then it's quite easy. It's quite easy to find the various things. So x looks like Ts minus T to the 6th. That means there's a similarity variable. Now I'll put the singularity back in, and so forth. Okay, so you get that. Okay, so now why is this useful? This type of analysis is incredibly useful in if you're trying to prove that the singularity happens. Okay, because if you do this, you get an ODE for this function. Okay, you get just an ODE for that you can solve in a certain domain, unbounded domain, because you're locally very close to the singularity. So the idea of the proof is that you go into the new time scale, and then all the other terms that you ignored will have Ts minus T to some power that's smaller than the others. and then you need to show that that is valid, that extra bit is a series that converges as Ts, T tends to Ts. Okay, that's how you would prove it. Which it's been done for simpler equations.
You only care about that if you care about infinite time.
If this happens, it means you cannot integrate for all time,
Oh, okay.
right? It means things would. Now, of course, I was being maybe a little bit too hard on the equation. This will happen in very extreme values of the parameters. Okay, there's a lot of parameters where this will not happen. Okay, so that was what would happen if things go singular, and there is this delta in it. So the question is, can I get a parameter-free equation? And I think that goes back to your question, Sarah, about the nonlinearity, how big the nonlinearity is. Because in this equation, right, in getting this equation with the deltas, I allowed the interface to be as big as the thickness. Okay, so by doing that, I sacrificed nice mathematical properties like global existence and so forth. Okay, now suppose now I don't allow it to be as big as the thickness, but I'm just going to allow it to be almost flat with a little amplitude, and I want to search for the first amplitude which will give me a nonlinear contribution. Okay, so I want small amplitudes, but not small enough so that it's linear. I want some nonlinearity, so I'll get a quasi-linear type problem. How do I do that? Well, I know that h equals 1 is an exact solution of that equation, so I put an alpha times h there. And I'll look for an alpha that will give me some kind of nonlinear balance. So if I do that, right, so you just take this, put it into the equation, and just differentiate it. This is what you get. I'll get a term, d by t1, and then with an alpha, and then this is, I get a 1 times that, and then a delta times a bunch of stuff that are linear, right? So this whole thing becomes linear now. The only nonlinearities are this times this and then higher order. Right? So if I look at this, what do I see? Well, alpha is small, so the leading order terms, let me underline them. This and this. Okay? Everyone agree? That's the alpha terms. Those are the leading order terms. Now, before doing anything weakly nonlinear or anything like that, those two terms were what gave me the shock formation. Right? It's what gave me the hyperbolic equation. But now, since they have constant coefficients, I can just go in a frame of reference, moving with speed, whatever it is, 2, and get rid of that. Okay, so in a frame of reference, moving with speed 2, so here's the equation again, right? So clean it up a bit. So this is the leading term, then the alpha term, the delta term. So when alpha equals delta and in a Galilean frame, right? And the new time scale, a smaller, longer time scale, right? Then I can get this equation. So what's nice about this equation is that, again, it has the same linear properties as the previous one. The nonlinearity is just the Burger's nonlinearity, just like I have in the Burger's equation. But now I have a regularization which is exactly absolutely fine, right? For derivatives, this can be bad, right? This could be negative diffusion if R is bigger than 4/5 cot theta. That's a classical result. And then this term will make things unstable too. Okay? So, by the way, if I switch this off, then this equation is the simplest one-dimensional PDE that gives chaotic spatial temporal chaos.
I'll be back on tomorrow.
No, you're controlling all the chaos tomorrow. So, okay, and then if you add this, you can prove global existence and all these things. So it's all very very nice. So, okay, let me now do something else. So, I guess I'll say something else if, yeah, so this equation, I mean, you can actually make it more canonical by rescaling, and this can be plus or minus depending on whether you're above critical or below critical. Okay, so if you're below critical, no electric field, everything is stable. Okay. Now, the question then is the following. So what did that do? I mean, it sounds like I did a lot of things that sounded uncomfortable, or they kind of were to me, right? I put the delta there, and then once I get the big delta equation, I then linearize and do all these things. So the question is, can I start from the Navier-Stokes equations and get this equation directly? Okay, kind of start with the Navier-Stokes equations and go directly for this equation. And of course, you can imagine that you do. The motivation on how to do it comes from the fact that I had the Galilean transformation and then another slow time scale. So that means multiple scales. So let me do that next. Okay, so let me. So yeah, ignore the first part. I already said it. So the idea now is to look for a solution, directly look for a solution of the exact equations, the Navier-Stokes equations, where I will do multiple scales in T. Right? So I have a delta T, T by T1, delta squared, T by T2, and so forth, and also looking for long waves. Okay, just start from the Navier-Stokes equations and do this. So the objective is to get this equation, which is parameter free. Okay, let me just mention the strategy a little bit because we don't want to waste time with the algebra. So the idea is the following. I will assume a small disturbance of size big delta. I don't know it in terms of little delta yet. Okay, that's my starting point. Then I want to find this big delta as a function of little delta so that nonlinearity will enter weakly into the problem. And in getting there, I will have to do a Galilean transformation first and then pick up the nonlinearity, just like we did with the other equation. Okay, so at the nonlinear stage, so the key to this is to pick the delta to be exactly the right value to give you nonlinearity, because if the delta is too small, then I get a linear equation which will grow exponentially in time, and that means I should have picked a bigger delta, right? If things are getting nonlinear. So, yeah, I don't know how much of this. I mean, like I said, I'll give you the notes. So let me just say a little bit about it. So the h is going to be 1 plus big delta h. So once I do that, I need to get the size of the velocities which are induced. And the way I get that is to go to the tangential stress balance, which was here. Okay, and I know what the leading order is. It's my u bar plus something u tilde. So I need to find the size of u tilde so that I get a balance here. And if I do all that, then I find that u tilde looks like delta. Okay, so if I make a small disturbance, this is, by the way, universal, whether you're doing linear or nonlinear or whatever. The moment you do this, a disturbance of order big delta, this is the size of the induced flow. So here's my expansions. Again, I'm not assuming anything, right? I'm just looking for the delta. So u bar plus big delta, u1 plus delta, little delta, big delta, u2, and so on. This is due to the long wave, right, the v. It's little delta times the size of the u. And then the pressure, of course, is big delta, because that comes directly from the size of the h, right? It comes directly from the interfacial disturbance in the normal stress balance. So if I do all that, okay, and this is the normal stress balance. Remember before there was an S0 minus 1 there. Well, now this is small, right? Because S0 is 1 plus delta h. So then, okay, I don't know what epsilon is. I'm just doing it systematically again. And then I need the balance here, so I will pick up what epsilon is by balancing all these terms. And here's the resolution of that. Okay, so in order to get a balance, the perturbation pressure has to be big delta as well. So we have this. So if we start with the Navier-Stokes equations and put all these expansions in them, okay, then the kinematic condition will just give me the traveling wave. So this is the first time scale, right? The delta times d by t1. So that will give you the traveling wave. So it's kind of very similar to what we did before. So let's see, how much time do I have? Okay, because we started a bit late. Yeah, I don't know how much value there is in going through all the details, but what happens? So the idea is what happens is that at leading order you get the Galilean bit, and then at the next order you determine delta by going to the kinematic condition. Okay, so maybe I'll show that. Because I want to do one more thing, so I want to kind of, yeah, I mean you can solve for U0, U1, V1, and so on, and the key is the kinematic condition here. Okay, so the key is the kinematic condition here, where if you do all the expansions, okay, this will be your next time scale, the next slow time scale. The leading order stuff will disappear, right, because of the Galilean transformation. And now you have enough information to determine what delta is, because the idea is to bring nonlinearity at its weakest form. That's the idea. In other words, HHX, okay? And that would be this term times that term. Everything else is small. Okay, so if I do all that, then I find big delta is little delta, and of course, like I said before, right, I could have started this whole session with this. And then you say, oh, well, where does it come from? Of course, it will work, but in order to get there, you need to do the expansions. Okay, so this will give me the equation exactly as I wanted. So there's a lot of algebra, and not only is there a lot of algebra, but I made a mistake too, and I'm missing a factor of 4 there. So it has to be there, but I think I did this a couple of days ago, so it was. Sarah will find it. Okay, let me switch gears a little bit to talk about something a bit more complicated in the following sense. In all the problems we've seen up to now, we had a thin layer with a thick layer, but the thick layer was electrostatics. It was just Laplace V equals 0, and a simple Dirichlet-Neumann map fixed everything for us. Now I'm going to assume that I have 2 fluid layers, right? Fluid 1, fluid 2, and one of the layers is thin. So for example, this could be water, oil, and you're in a quad device, let's say. In fact, the only reason we did this problem is an experiment in a quad device that had some results that weren't explained. And hopefully I'll convince you that they are explained now. So what do I need to do? Well, I need to solve the Navier-Stokes there and there in a shear flow, right? So there's a simple shear flow. And find the evolution of the surface. Look at the waves that form at this surface and compare them with experiments. Okay, so what's the complication? Well, everything in this layer we've already dealt with. Okay, we know how to do that. You go into this, you scale your variable, you stretch it, you analyze the duplication. Here, however, I need to solve the Navier-Stokes equations. And again, the natural length scale now, right? The natural length scale is the thickness of the channel. The natural wavelength is also the thickness of the channel. Okay, so now I'm in a situation where I don't have one over delta. It will be 1, but the layer is thin, right? So the wavelength is order 1. So this region will be an elliptic region. So let's see what happens. These are the Navier-Stokes equations. There's nothing new here. There's no gravity. I got rid of gravity. You can include it. Doesn't complicate things. And I non-dimensionalize using region 1 variables. It doesn't matter. There is an exact solution, and here it is. I think Darren wrote this down earlier today as well. So in fact, this is the stability of the solutions Darren was talking about earlier. Okay, waves into the ball. So this is the base state. So again, what I want to do is do this very systematically, right? So in the scale equations, after I non-dimensionalize, the shape, the upper wall is at y equals 1, the interface is at 1 minus epsilon, where epsilon is small. Okay? That's the only small parameter in the problem, nothing else, just that. So I want to deflect around that, as shown down here. So I want to deflect the interface. So the position of the interface is at 1 minus epsilon, that's its mean value, plus delta, big delta times h. I don't know what delta is. I need to find it. Okay, this is different now because it's coupling flows. So, first observation, if I do this deflection and I work out the basic state, right, as I approach the interface from region 1 variables from below, and I subtract the basic state velocity as I approach from above, right? I mean, I know if the interface is flat, they're equal. But if I deflect and I look at exactly these fields, then they jump by order delta. So that means the moment there's a deflection of order delta, there will be some velocity disparity in the two layers of order big delta. Okay? So, what happens next? Well, next I need to try and analyze things, right? I need to do stretched variables. So in the thin layer, now it's slightly different than before. My x is order 1, right? d by dx is order 1, that's the thickness of the channel. But there's a new variable I need to introduce in the upper layer, which is 1 minus epsilon zeta, where zeta is a new order 1 variable. Okay, that's like my boundary layer variable. In terms of zeta, the interface is here. Is that 1 minus delta over epsilon h. And then I said, oh, this is order 1. Why? The reason is that I'm assuming that big delta is going to be small compared to epsilon. And that's weakly nonlinear, right? Epsilon is the thickness of the layer, delta is its amplitude. So it needs to be smaller, because I'm shooting directly for a weakly nonlinear solution. Okay, so if I do that, then my Navier-Stokes equations does this. And again, I don't know what the velocities are. I'm going to try and find them. Okay, so this is what the Navier-Stokes equation looks like in the upper layer. Okay, so d by dy gets promoted, right, by epsilon squared, two derivatives. Then there's a pdx, right? Now, then the question is, what's the pdx? Well, the pdx is going to come from surface tension, right? I have to include surface tension, otherwise things will not be well posed. So I know that the curvature is this, delta over capillary times big H, this is order 1, and the jump in pressures, now I have two pressures, not like before. The jump in pressures is equal to that. Possibly P2 is there, the P1 is there maybe, we don't know, right? So we expect the capillary number to be small, from a surface tension, and then that immediately means that P2 in the upper layer is going to be much bigger than P1. Okay, so we will, the P1 is going to be of order delta, and P2 will be of order delta over capillary. And we'll show this. We have to confirm this. Okay, so if that happens, if P2 is of order delta over capillary, then I can go back to this equation and get an estimate for what the U2 should be. And here it is. Okay, so the U2 is of order epsilon squared times big delta of the capillary. V2 will be epsilon smaller, right, because of the long wave. Okay. Next, I need, and again, to resolve these puzzles, you need to decide how much physics or how many kind of phenomena you want to include. So what I really want to do, right, what I really want to do is get an interaction between the thin layer and the thick layer. If I don't, it's like doing just thin layer asymptotics in one fluid that doesn't fall within the experimental parameters. So I definitely need that coupling. So I go to the tangential stress balance. I haven't used it yet, right? So I have to go to the tangential stress balance. And here it is, written in full form. We haven't seen it before. Variables 2 in the liquid film and in the main part. Now, the right-hand side has this size. Right? The right-hand side has this size. Biggest term is that. Right? That's the biggest term because it gets promoted 1 over epsilon because of the d by d zeta. So I'll get that term there. That's the right-hand side. But I already know what u is, so I can put it all together, and there it is. Right? So this is what the right-hand side is. The left-hand side is the disturbance in the velocity in region 1. But I already saw that the jump in the base states at the interface was order delta. So that's the disturbance that will be promoted in region 1. It's going to be size delta. So the left-hand side is size delta. Again, where does that come from? Well, it will come from this. Right? But now d by dy is not promoted because it's a thick region. Right? So I'm dealing with a thin region and a thick region. So, so that gives me this balance, and immediately I get that the capillary number should be order epsilon. It's a very good question that no one has asked yet, and that's the following. When I did this disparity in velocities, and I found it to be order big delta, I loaded it onto region 1. Now you could object and say, well, why isn't that the disturbance that you would see in region 2, in the thin film? Perfectly valid question. The way you see that, you do the following. You say, okay, suppose it was. And if you suppose it was, then if you do, then the leading order solution in region 1 would be d2u dy squared is 0. So that means it's ay plus b. The leading order solution in the tangential stress balance would be du2 dy is 0. So that means a is 0. So you just get a trivial solution. Okay, so it won't be there. So it's all consistent. Okay, so what's next? We're almost there. I know Mark is getting nervous. We're almost there. So the capillary number is order epsilon. So that will give me a coupling between these two problems. It's a very, very unusual problem, actually, as you will see. So to get a final equation, I need to go to the kinematic condition. Because I also don't know what big delta is yet. So here's my expansions. And by the way, the kinematic condition, I could choose to evaluate from region 2, from the film, or from below. Doesn't matter, right? The vertical velocities are the same. but it's much easier in this case to do it from region 2. So here's what happens. So I'll get the V2, then the delta times HT, because the size is delta. This is all base flow stuff, right? This is the U bar. And then there's the disturbance there, times delta times H. Okay, and then I need to look at what the biggest terms are, right? So the biggest terms, if you think about it, are going to be delta squared times, delta times delta. That's the biggest nonlinearity, and here it is. Okay? Everything else is smaller. This is smaller. It's a higher order effect. But the left-hand side is epsilon squared delta. Then I get delta HT plus this guy. That's the biggest term in the equation, but I can get rid of that with a Galilean transformation. Okay, so go in a frame of reference moving with the undisturbed velocity at the interface, and then get your microscope out and do the local dynamics. And then this is the nonlinearity. Of course, to get a non-trivial solution, this term has to balance this term, and there's my delta, right? So delta is epsilon squared. So what does that mean? It means that the layer was epsilon, the disturbance is epsilon squared. So it was weakly nonlinear. So that also confirms the previous assumption, right, that delta over epsilon was very small. Okay, so it's epsilon squared. So this is very much in the spirit of the KdV, if you ever saw a derivation of the KdV. Okay, so what's next? Well, this is my equation. This is my equation, and now it's much more complicated. I need to find this thing. This is the expansion. So now I have delta. I can do everything in terms of epsilon. It's honest at this point to just use everything in epsilon. So that's region 2. That's region 1. So we can see that region 2 has a one order higher velocity. Perturbation velocity. Okay, so if I go through all the various things, I can solve in region 2, because P2 I know is simply a function of x and t. I know it in terms of big H, so I can integrate, right? So I can integrate this. Therefore, I can get V2 and put it back into the equation, into the kinematic condition, to get a single equation. Now, of course, there's a slight problem, right? Because there's a constant, a new function, rather, a, that appears in V2. So if I look at this, right, this is known, this involves H. This I don't know yet, and my kinematic condition needs V2 here. Okay, so I need to find A to close this equation. To get a single equation, I need to find A, or the A dx. So let's go find it. How am I going to find it? Well, again, the only thing I haven't used is the tangential stress balance. I mean, I did orders of magnitude, insisting that the two